let's go through this process. So remember, with you guys, I can't remember, it's different with everybody. Did we actually build a table yesterday?
Yeah.
Okay, and we started to do a little bit with it, but not very much, right? Okay. So here's what I want you to do on this assignment. I don't even want you to do what they tell you to do on here. I want you to do, for problems 4 through 7, those are the ones I really want you to do. I want you to just build a table on a separate sheet of paper. Here's graph paper if you want to use graph paper. Build a table and do a sketch of the graph. Okay? And so I'm going to show you how to do that. So close those up. I know you want to, I'll get you going, I promise, but close them up and look up here. Let's put away earbuds, phones, all that stuff. So recap of the table, right? The table is going to look like this. When you draw the table, you're going to draw it across the paper, make them big, waste paper on this. And you're going to draw at the top, it's going to be the x-axis, and then there's going to be a row with x values and a row with y values. In calculus class, we'll add 2 more rows to that with derivatives of the function, which means nothing to you now, but it will later, and it'll just be the same process, but we'll add more information. Okay, but for now, this is pretty good. So our goal then is we want to be able to just put enough information on this table to be able to make a sketch. And there's really 2 main places where we start with this. We want end behavior and we want x-intercepts. Okay? Let's start with the x-intercepts. So how do we find those? Here's my function. How do I find x-intercepts? How's that going to work? Let me ask you this. What's going to be, for every x-intercept, what's going to be the y value?
1.
No. X-intercepts are on the x-axis, right? It's going to be 0, right? So every point on the x-axis has a y value of 0, doesn't it? Because it's not up or down at all. Agreed? That's what y tells us, how far above or below the x-axis is, right? So then what's this mean? Well, f of x is just a fancy name for y, isn't it? Right? And if we want y to equal 0, we're just going to set f of x equal to 0, right? So to find the x-intercepts, we're going to take this function and set it equal to 0 and solve, right? That's how we ask the math gods a question. We give them an equation, and then they tell us the answer through algebra, right? So here's the equation that we're going to solve. We want to set the function equal to 0 and find the values of x that make that happen. And those are going to be the x-intercepts. We want to find the x values that make y 0, right? This is really easy because the function is already factored for me, right? It's already factored. I've got, what are my factors? Well, I've got a -1 out front. That's a constant factor. That doesn't really help me. But the other factors are x plus 1 and x minus 2 squared, right? Now, think about, let's go back and kind of put this all together for a second. This will be helpful. The zero product property reminds us of something. If I'm going to multiply stuff together and get 0 for an answer, what's the only way I can do that? What do I have to multiply by to get an answer of 0? 0. The only way it can happen is if I'm multiplying by 0. Otherwise, no 2 numbers will multiply to 0, right? So the only way for this to work is going to be one of 2 things. Either, one thing would be either this factor equals 0, or the other possibility in this case would be that factor equals 0, right? That's the only way that the product of those 2 factors and -1 is going to be 0, right? So what's going to be the x value that makes this factor 0 so the product can be 0? -1, right? So one solution is going to be x equals -1. What's the other one going to be? Right? Did we need to write all that down? Probably not. We could just look at this and say, what's the x value that's going to make that factor 0? Well, -1 plus 1 would work, right? What's the factor that's going to make that one 0? Well, 2 minus 2 would work, so x would equal 2, right? And then those are the numbers that we're going to put on our table, right, for the x-intercepts. So let's add those. So we've got the point x equals -1 is going to be to the left and 2 is to the right. So in our x row, we're going to put the x values -1 and +2. And those go with y values of 0 And so now remember, we gotta tilt our head this way to see those as ordered pairs. -1, 0, and 2, 0, right? That tells us something. So we can already start on our sketch, right? Our sketch is now gonna look like, so if this is the x-axis on our graph, that's -1, well, maybe this would be like the y-axis then, right? So back at -1, we're gonna have an x-intercept, and out here at +2, we're gonna have an x-intercept. So that tells us something about our graph. We just need some more stuff, right? So now we need to know what's it doing in between the x-intercepts, because we gotta know if it's gonna loop up or down, right? Does the function live above the x-axis or below the x-axis in between these two, right? How many places could this function cross the x-axis? 2, exactly 2. Could there be another one? No, there can't be. Because if there were another one, we would have had to have had another factor up here in our function. There's only two zeros of this function, right? And so there can only be 2 x-intercepts. There cannot be a third. There are exactly 2. That's going to help us. All right, so we want to know what's going on in between. So we're going to pick a test value, a test point, right? What's a value of x, a convenient value of x between -1 and 2? The easiest one would be probably what? 0, yeah. Let's pick 0 for our test point. And let's go up to our function and see what happens. So if we evaluate our function, f of x equals, if I put parentheses around all the separate factors, it's -1, that's what that negative sign is, right? Times x plus 1 times x minus 2 squared, right? So f of 0 is going to give us what back for a sign? I don't care about the value, I just want to know what's the sign going to be, right? So, Dalton, what are the signs going to be of each of these factors when x is 0? What's the sign of -1 going to be? Well, hold on now. What's the sign? That one's just a constant factor. It's not even going to involve the x, right? That one's just the number that's out front. It's never going to change. What's the sign of -1? Okay, it's negative, right? Okay, now this one we got to look at. So if we plug 0 in for x, what's the sign of that factor going to be? Positive, yeah. 0 plus 1 would be positive. What about this one? We got to be careful. If I plug 0 in here, I'm going to get 0 minus 2, but I'm squaring it, right? When I square any number, what's that going to do to the sign? It's going to make it positive. So this one is always going to be positive, and that one's always going to be negative. The only one that really could ever change is that middle one, right? What's the overall sign going to be here then? Negative times positive times positive. What's that going to give us? Negative, yeah, right? And so down here, we know that's going to be negative, which means it's below the x-axis, right? So we can go down to our table, and in between these two, let's just put a point. It doesn't even really have to be at 0. It just needs to be in between that tells us it's going to loop down below, right? Okay, the only other thing we need to do now is get the end behavior. So we did this one way yesterday, right? We talked about how if we were to multiply this all out, we could figure out what the leading term is going to be. I'm going to show you another way that you might even like better, okay? We could do the very same thing we did here, but let's just do it with positive infinity and negative infinity, right? So what if we plug positive infinity into our function? We know we're going to get an infinite result, but what's the sign going to be? Let's look at the signs of the factors. What are we going to get for the first one?
Positive.
Well, it's always, first one is always negative, right? Because it's just a -1. It's a constant. It's never changing, right? What about the third one? Well, it's being squared, so it doesn't even really matter. We can think about it. A huge number minus 2 is what? A huge positive number minus 2 is what? Positive, right? But it doesn't even matter because it's being squared anyway, so it's positive. What about this guy right here? A huge positive number, like infinity, right? Plus 1 is what? Positive or negative?
Positive.
Positive. And so the outcome is going to be negative times positive is negative infinity, right? So out here at the edge, when we go out to positive infinity to get our end behavior, the answer is negative infinity. So what's that tell us? That tells us that it's going, the end behavior is down on the right. Okay? What about the left? Let's put in negative infinity. Well, the first one is negative. The last one, because it's being squared, any negative number, doesn't matter how big, if I square it, it's positive. What about this one right here? If I take negative infinity plus 1, is that going to be negative or positive? Negative. So now I get negative times positive equals what? Negative times positive. Positive, because I have an even number of negatives being multiplied. So I get positive infinity out here at the left end behavior. When x goes to negative infinity, y goes to positive infinity. So that tells me that the left end behavior is up. So now we can fill in the rest, right? How are we going to do this? We know that the function is going to go, it's got to end up going down on this side, right? So let's do the right part first. So it's out here. Can it do this and then go down? It can't. How come? It's got to stay below. That would mean we'd have to have another x-intercept, right? So that can't happen. So what's it have to do instead then? Yeah, it's going to go up to here. It's got to touch the x-axis, but it's just going to graze the x-axis and then go down, right? Does that make sense? Because it can't cross it again. What about the other side? On the other side, it's got to go up. So it's just going to do that, right? It's going to go through the x-axis and keep going up to the left. You get the idea? So it's like a puzzle. We're just going to use this little bit of information on the table to fill in the blanks on the function. One other thing I'll tell you here that it's not like this is such critical information, but it comes up on this assignment. Now, I don't even care if you really do that part, honestly, but what do we call these things? These are called turning points because the graph is turning from going down to going up and from going up to going down. Those are turning points, right? Turning points come in two flavors. They're either going to be peaks or valleys. A peak we call a maximum, a valley we call a minimum, right? And so this is an example of what we would call a local maximum. I'll tell you why in a second. This is what we would call a local minimum. Why do we call it local? Yes, ma'am.
Goes forever.
Okay, because it's local because, yeah, the function goes forever, and local just means around you immediately, right? Like a local issue is one that affects people in Pendleton but not people in China, right? So this is a local maximum because if an ant's standing here, relative to his immediate surroundings, he's in the highest place, right? But there might be other places, and there are other places on the function that are a lot higher, right? Same thing down here. The ant is standing in a valley, so he's in the lowest place locally, but far away there might be places that are lower. What if the function did something like this instead? Let's say we had a function that went like that. What's that going to be? That's going to be a local max, right? What's that one going to be? A local minimum. What's that one going to be? It is going to be a local minimum, but we can even do one more than that. We could say that this one is special. This one is going to be what we call a global minimum. How come? Okay, because it is the lowest point anywhere on the graph. Agreed? An ant could stand here and say, I am at the lowest point, period. There's no other point anywhere on this graph that's lower because the end behavior goes up, right? Does that make sense? Okay, I think you got it. Want me to do one more or you want to just try this? Think you want to try it? Have at it. If you don't have one of these, grab one. Here's the instructions. Only thing I really care about is when you do numbers 4 through 7, do them on a separate piece of paper and do this stuff. Make a table and make a sketch, and I don't care about the other stuff on here. Okay? Make sense? All right. Have at it.